Good afternoon. It's 12:15 on the 19th of October 2005, and this is probably interview number 10. Burke, would you like to make an introduction?
Right. David, is this the tape?
Okay, go ahead.
Dave, there's so much on the web today that can help with the mission that we have in mind. And I just wanted to give you some examples. And I will spend time for future meetings picking what I think is the best that will further it. And since some of these I've just come across, I thought we would do an introduction today and then see where we go from there. Here is one that I am particularly attracted to. It's called Exploring Sugarscape, Comparing the Distribution of Wealth in the Sugarscape with the United States. And Sugarscape is a simulation. So I'm just going to run through some of the slides as an example, and then I'd like to switch to another site to illustrate something. So here we have that. Now we'll go on to the next slide. Agents in sugar space live to accumulate sugar. The more sugar they have, the happier they are. They need sugar to reproduce. Let's take a closer look. NetLogo, which is a statistical training program, has a wealth of models based on the Sugarscape. It provides us with good opportunity to examine a model in greater depth, examining the data produced by the model, making comparisons of the wealth distribution of the agents with wealth distribution in America. You can begin to see how this is important to what you referred to as Burke's Law, and how to illustrate it in a different manner. What is wealth? And wealth consists of the value of tangible assets plus financial assets minus debt. It's a bit simplified in Sugarscape. Wealth equals the total accumulation of sugar. There are no commodities, minus the agent's metabolism rate. An agent's wealth increases each iteration by the amount of sugar it finds, minus its metabolism. And this goes on in this manner, and we're going to be able to do some simulations and illustrate what happens over time. And I want to study this to decide which of the ones that we in turn take a look at.
What is this site aimed at?
Well, the site is aimed at, let's just see if we can see what happens here. Oh, I lost it. This site is the NetLogo Learning Lab, the resources for NetLogo Modeler, and it's the Institute for Modeling Complexity. I haven't checked further, but the chances are it's developed by Yuri Walensky, who was a disciple, I guess still is, of Seymour Papert, who wrote Mindstorms. So the whole purpose behind the thing fits in with what we have in mind. Although this is dealing with mature high school students, but Papert started off in saying how he could introduce very young children.
Could you bring up the question there, why we model? The third question there.
Yes, all right. Now this will be a PowerPoint. I think it's very exciting with what is available on the web. That
Go ahead.
model making is an attempt to understand the world. And of course, the causal is that. Now if you notice...
Can I read that?
I'm sorry, go ahead.
Children make models of the physical and technical world they know, endlessly building and rebuilding with clay, mud and water, blocks and bricks. Children model the social world around them and teach themselves how to get along in it, experimenting and exploiting without risk by their play with dolls.
Right. Now you notice this character. And this is an artificial intelligence operation, Microsoft. And in turn...
That's Einstein.
That's Einstein. But you see, that icon, which really becomes an icon for science, gives an impression of science that of certainty. And this is, we're working on an icon that will give the impression of of science with regard to uncertainty.
And the door we heard opening was Einstein entering.
And when I shut it
Can-
off, he will leave.
Yeah, let's do that.
You would like
Can you
to
do that?
demonstrate that?
Yeah, just to see where the sound came from. I thought there was
all right.
somebody next door.
Well, then I'm just going to turn this off. Just a
Okay.
moment.
Okay, and can you bring it back?
All right, now we'll bring it back. He'll be back in a moment.
Enter Mr. Einstein. Dr. Einstein.
Well, here he is. Isn't that clever?
Very clever.
Right. All
Okay.
right. Now, do you want to read that?
Modeling, however serious, enshrines an element of play. Scientists are incessantly saying to each other, let's play around with that. Modeling is the quintessential way of playing with the way things might work and might be. The play and the seriousness feed to generate the energy of modeling. Not quite grammatically correct there.
Now listen to scientists talk about their work. Whatever the field, they talk about their models or patterns. Okay? Models are not complete in every detail. Models leave out trivial details. The art of model building is the exclusion of real but irrelevant parts of the problem.
Mm-hmm.
You can see how this is a good introduction to the acausal.
Mm-hmm.
We're going to go over to that in a moment. Model building entails hazards for the builder and the reader.
The builder may leave out something genuinely relevant. The reader, armed with too accurate a computation, may take literally a schematized model whose main aim is to be a demonstration of possibility. Models isolate the features of the something modeled which make a difference.
Now, 3 levels of performance of models: the performance of objects, idea models, the behavior of elaborate systems, systems models, and a kind of theory building models.
Will it fly? A paper airplane is a model that will test an object or design of an object. Wind tunnel testing of wing designs helps engineers analyze turbulence around wing structures at scale.
Now, the advantage of modeling an object's performance. Models are means to trial and error, a way to make mistakes safely and relatively cheaply. Models make it possible to work out bugs for objects that must work the first time. Think of the space program. Spacecraft are models because they can be worked on as they fly past Jupiter.
The scale effect. Scale models always have the problem of the size of the object creating different problems than those in the small scale. Scale models of wings do not show problems with turbulence because of the viscosity of the air and the size of the object. Big rocks disturb the flow of the stream disproportionately more than small ones.
Now, 1979 scale model of Disney's Epcot Center. And he says, see the book in class. There's slightly more to this.
This is aimed at high school students?
Yes, yes it is.
Maps are models. Good maps are ones that eliminate those real but irrelevant parts of the problem. Systems modeled by maps usually have great quantities of data that must be put into relation to each other. This type of model tries to predict outcomes. The most complex systems for which models are being built are the weather and the economy.
A 48-hour model of expected precipitation, and that's the type of style they use. A New York City subway model. Models in theory making. A model of a complex system allows the incessant interplay between prediction and correction of the model.
The contribution of models. Models hold information and communicate it. There's a quote from Linus Pauling, Nobel Prize winner in chemistry 1954. The construction of the model may represent the development of a theory, and with a model it needs to be a precise theory. If you have fuzzy, vague ideas, then you find that you can't build a model because a model must be precise.
What purpose will the model serve? Well, will it help you gain an understanding of a phenomena or a new topic? Will it be a snapshot of an idea you have? Will you use it to gather data to predict an outcome? Thinking through your goals at the outset helps you to structure the process creating your model.
What is a scientific model? Illustrative models are meant to provide some kind of visualization of a scientific process or system. Examples include models of the solar system, paper models of DNA, deribonucleic acid, transparent human bodies. These are scientific models because they capture an aspect of a scientific system or process and help you understand it in a new way.
Analytical models generate solutions that predict behaviors of systems based on a given set of conditions. For example, include a physics student might use a formula like x equals 1/2 at 2 as a model of how positions depend on time and acceleration. A math teacher might describe a cellular automata using a series of mathematical formulae. A biologist might model a population growth rate with a formula of R equals F plus S.
Now, go back for just a second. The 1/2 plus AT2 is 1/2 plus AT squared.
Square, yes.
Yeah, okay.
Right, I'm sorry.
That's all right. It didn't look like a square. Simulation models. Simulation models have become a dominant form of modeling with the widespread use of computers. The modeler describes underlying mechanisms and then lets them run over time to see what happens. Examples include weather simulation models to help with prediction, large-scale ecosystem models used to study effects of small variations of starting conditions, economic models which examine the distribution of wealth.
Now, in our case, we're interested in a simulation of an economic model. It goes far beyond that, but because inequality is something that plagues us all, it's by introducing children at a very young age to a model that can help them grasp how inequality is generated is extremely important. And the purpose of introducing them at a very early age is to recognize that the model has no cause, that these things happen. That does not mean that you won't have a right to make decisions, but the end result will be virtually always the same, regardless of the decisions you make. And this sounds rather fatalistic, and it isn't, in that once you understand how the model works, you then can act in such a way to increase the benefit for all. And I hope we'll be able to show that.
Defining your simulation model. Using simple rules of interaction of agents, you will be able to build dynamic complex systems. NetLogo enables you to define relationships among individuals in the system without using complex mathematical equations like those typically used in analytical models. Constructing your model will be challenging because you'll have to decide what facets of the system you wish to use and which you choose to leave out.
Now, this is extremely important, not only the statement, but its illustration that the type of help that we can get with our problem on the causal from people who are quite familiar with the problem. So it means we're not alone. It means we might have to travel, we might have to go elsewhere. But because we've worked in relative isolation and it's not easy to be in physical contact with these people, nevertheless they exist, they're thinking of related problems, and what we're doing is of interest to them. Classification scheme for simulating models. This scheme was proposed by Rogarden and is based on the purpose and the amount of real-world complexity involved. Minimal models for an idea or idea models, minimal models for a system, and system models. Now, by and large, we're working with a minimal model, as we'll see shortly. David, I think this is a good introduction in some respects to what we're doing.
Idea models, Gedanken experiments, seek to capture only the most fundamental parts of the system. Idea models may be used to illustrate a general principle, or they boil things down to the most relevant parts. Examples of idea models are predator-prey relationships in zoology, supply and demand economics, molecular motion.
Also, it could be a model involving what happens in a game of Monopoly, or in business in general. Now, minimal models for systems incorporate some aspects of an actual system without incorporating a fine level of detail about the system. That's comparable to a map. Includes enough specificity to narrow the applicability of the model without including so much detail that it only applies to one particular case. Again, this comes into Ashby's concept of requisite variety. We have to get things down to a model because it is necessary. The world is too complex and we can only operate according to models. Examples would represent generalized systems like herbivore grazing on a grassy landscape, store owners pricing baked goods.
Minimal models for systems.
I think we've done that one.
Yeah, we've done that one.
We've done that one.
Sorry.
Go ahead, Dave.
Okay, here we go. System models. System models are usually built as a collaborative effort among many researchers. Together, the researchers synthesize individual findings into a huge model. Systems models require extensive data collection and intensive effort. They often require years to build, even with many experts participating. An example would be a model of growth, movement, and interaction of all the plants and animals in Yellowstone National Park. Another example is perhaps one of the most complex models ever built, based on the work of Jay Forrester at MIT. It was done by a fellow named Dennis Meadows, and it produced the book Limits to Growth, which was a simulation of the world over the period of 1975 to 2025, attempting to compare population growth with the food supply and the growth of economics and technology. It was basically a doomsday forecast, but at the time, probably the most complex econometric model ever built.
What lessons do we learn from that?
An important lesson that I think was learned from that was the criticism that the modeling received, and the modelers, the people who were doing the research, wanted to trigger a debate among a larger, wider audience of experts in the field of econometrics. And the debate triggered additional research, and I think in that particular case, because it was a doomsday forecast, most people looking at it said, oh no, we're going to be able to fix things. Every single projection made by that model was a disaster for humankind, except the model that put a stop on or slowed down the rate with which technology is moved around the world. The culprit, as far as the modeling, that model was concerned, was technology. Technology that produces air pollution, and technology that produces jobs, or in some cases it reduces the number of people working. So I think that was the lesson of create a controversy, and mankind will learn a lesson.
I think it also pointed out that as we're really not that good at predicting. We still need models. Mm-hmm. And the fact that the Club of Rome model that you're referring to was not that good at predicting, it is still a necessary activity because we all have implicit models. At least that model, and their challenge was that if you're criticizing our model, what's your model?
Yes.
What are your assumptions, and what do you predict? Mm-hmm. So I think the modeler's reaction to all the criticism, rightfully obtained, is that's fine. But here we have put our assumptions and our model on the table. Mm-hmm. Just don't throw stones at it. That's fine.
Yeah,
but well, rather even better, what are your assumptions, and what are your predictions? Mm-hmm. Now your
incidentally, that effort, the work of the Club of Rome, triggered a worldwide increase in the amount of environmental legislation to control emissions, CO2 emissions, and reduce H2O consumption, because that was a major contributor to difficulties that humankind are experiencing.
So good came out of the model.
Yes, I think so.
Now, your project, your primary task in the month of February is to develop your own net logo model of a complex system. This will probably be an idea model. By Wednesday of this week, you need to provide us with written proposal explaining what type of model you want to create.
That's wonderful.
So I think it is wonderful that this is what's happening with high school students, and it's going to train them to think in a model way that was not available before. And we have this wonderful web, an interactive tool.
Beautiful.
Good.
Okay.
All right. Now, goals of this project to give you experience in programming models in NetLogo, to better understand the concept of CAS. Now, from my regrets is that I don't have another life to live, because I would like to learn NetLogo, because I think if I could have the time to master it, it would facilitate communicating what I perceive.
Yes.
But I don't know quite what to do about that.
Here you delegate that task. It's
Yeah.
like models that have been built by others. It's like building a website. You hire an expert to.
Now, it's really quite interesting that where we stopped last day was a quotation by Yuri Walensky, who is behind all of this. And I think that is rather appropriate. And
Yeah.
now let's.
You want to get the quote? Go ahead.
Now, if you notice this section, it says complexity in the social sciences. I'm a social
Not sure we
scientist.
can read that, yes.
Can you see that at
I
all?
probably can't read that.
All right. Here we're dealing now
Well, just
with
a second. Yeah, go ahead.
with swarm intelligence. What's meant by swarm intelligence? Now, let's just take a quick look at this. What we can learn from ants, and then they have a clip from Bug's Life, and then what's wrong with the movie, and it goes on from what can be learned from an ant colony. And there is a lot, and I hope, give a reference out of science to show what can be learned from an ant colony, and then apply it to econophysics and to see the overlap, which will also illustrate that the division between the sciences are artificial and can often be inhibitory in order to understand things. Now, here's a NetLogo exercise on swarm intelligence. Let's see what they have here. I don't think we'll go into this here, okay? All right. We are interested in economic models because we are looking at the problem of inequality and how it's generated. As we mentioned, this is from the Institute of Modeling Complexity, and it has to do with these resources of NetLogo. All right, let's just leave this for a minute, Dave. Now, I want to illustrate the overwhelming amount of information, yet how beneficial at the same time, why we must get this down to as simple factor as possible, because the amount of information available is so much that our brains cannot adjust to it.
Just read out, these are the categories of your bookmarks, right?
These are the categories of my Burke
Yeah, I
bookmarks.
can see those. You want to run down them until
All right, so I'll give you some idea. They're 3D, 3D because I'll give you some background. I'm interested in three-dimensional perception, and three-dimensional perception is a miracle. Why can we, with two eyes, and take two disparate pictures, giving each to each eye? How can we come up with depth? How the brain does that to this day, we don't know.
Okay.
The next one is Six Sigma. Now, Six Sigma is one of the things that will help in understanding the basic of causal.
Can you move the cursor down?
Six Sigma, and you see all these other websites associated with it. Six Sigma, you have to understand what Six Sigma means, and you can understand it by using the causal demonstration. AAAS is the American Association for Advancement of Science, who's interested in everything that we're doing because we're enhancing their aims. And the if we look over here, they have Project 2061. And Project 2061, they've set, as in your method, they've set the dream for 2061, and they're trying to see how far they can get in increasing scientific literacy. I'll carry down. The causal are all the subcategories pertaining to the causal project. Now, each of these, rather than just being a site, represent many other bookmarks. Decision making, demonstration, designers, direct writers, econophysicists, emotions, eugenics, all these things are relevant.
Keep going.
Evolutionary epistemology, those familiar with the art, all of these that you see there, sorry, are we off, Dave?
No.
All these we see here are people who will comprehend what we're doing, or some aspect of what we are doing. And to give you a specific example, for instance,
let's go back to the names. Are these the names?
Yes, there's a whole series of names or organizations. Here we have David Gooding. Now, David Gooding's work is particularly relevant because he has brought to the forefront, if you can come over here, the experiment as an instrument of innovation. Experience and embodied thought. Now, what is this? Is that most of us, when we think of an experiment, we think there's a hypothesis. You design an experiment. It tells you whether the hypothesis is right or not, and then you carry on. Gooding and his associates from 1980 on, roughly, saying that's the wrong perception of an experiment. You do an experiment, the experiment gives you some ideas, you go back and you do something else. There's a constant interchange. So you have to look at the experiment as a feedback mechanism. And he's gone into great detail at looking at the behavior of Faraday, really the father of an electromagnetic age. And this can carry on as we are doing. Now, what I wanted to do, there's a whole list.
Let's go back to some of these names here. I want to scan down.
You want to...
I'm just going to scan down the list.
All right. Ephraim Steinberg, and I go to his page. Alex Kasman, Alexander Bogomonli. He has an excellent setup for communicating a love of mathematics.
So Burke, all the hours that you spend browsing here, this is, you pick up these pointers, these websites, bookmark them, and categorize them as you go.
Yes.
Right? And that's how you're able to go back and find relevant references, and your bibliography here, your indexed bookmarks, represent many hundreds of hours of work.
Yes. And also it's reinforcing to show that we're far from being alone. It's
Very
just
good.
that all we're doing, as I think Newton said, standing on the shoulders of giants, all we're doing is taking a look at what is going on, what is missing, and what can we possibly contribute. I came to the conclusion, after particularly looking at and studying what children need, is that in the case of the sciences that have made the most effect on us, that they had their origins in what is available to the senses. And in what we're doing, it doesn't have. And we have to do something about that, and particularly before the child is 5. Now, if I carry down here, I want to show you, I mentioned Yuri Wilinski. So I want to, let's go to one of his sites. And I think, and this is where I took the quotation that we didn't, no, I don't know if we did. No, I didn't. No, but this is another article by him. All right, let's go back so here's how I follow. I know it's under a causal. I know it's under familiar with the art. I'll go down to Yuri Wilinski, and I want to find a demonstration here if I can. Here. Now watch. Okay. And here we have what is central to what we're doing. We just had an introduction to modeling.
Yes.
Now let's look. He refers to it as the Galton box. As you know, Galton referred to it as the quincunx. Quincunx. I refer to it as the acausal because by naming it the acausal, it brings into existence something that we do not consider, the opposite to cause. We do not have a word even to discuss it. So in that regard, we're similar to the square and flatland. When he got into sphere land, he could understand what upwards was. But when he came back, he couldn't share up with his colleagues because they had no access to it. So here, let's just examine.
Is there a demonstration here?
There's a wonderful demonstration. Just take a moment to load.
So tell us a little bit about this.
Well, this is basically the physical or the computer representation of what. Okay, so that looks familiar. All right, what this basically is going back to about the 1500s, and you might want to take that. The Chinese. And that's where we have to start with the origins of this.
And what is it used for? What is that?
This is what was referred to as the expansion, the binary expansion, and it is a way of representing what happens. And
what did the Chinese use it for?
the Chinese used it in terms of differentiating herbs for taste and such. I don't know enough about it to be literate,
Okay.
but
And what happens here?
well, but here we have now. Let's see how many boxes do we have? A number of rows. We have 12. Now I want to, in the coin we're designing, I want to have 11.
Right. Can you change that?
Yes, I'm going to change it, but it changes.
11 because of the outcomes of
Well,
the roll of dice?
Yes. Okay.
11 outcomes?
All right. We're there at 11.
Yeah.
Okay. Now, the reason for it is that if we have 11, we then can simulate the 2 to 12.
Right.
All right, now let's just run the setup. Here I'm going to run it with 75 balls, and it's going to be a fair game. Okay?
50-50?
Yeah, all right? And,
Oh, this is wonderful.
okay, now here...
You can change the fairness.
Yes, watch. Look what happens.
Oh, I'm sorry. Let me back up a little bit here. So as you change the parameters, the distribution changes.
But
right?
if I here let's
okay. So go back to 50-50. Let's see what happens.
No, it's still 50-50. Okay.
Now change it to
let's
something skewed.
All right. No, let's leave it like it is for a moment. Okay.
Yeah.
Let's run it slower. Okay. Okay.
Yeah.
Now, if you notice, we've got from 0 to 11. That's one. That will give us 12. I don't want.
No,
12.
it's 10 gaps. It's 11 gaps.
I want.
Yeah.
I want bins. Yes. Okay.
There's a bin from 0 to 1.
Okay. Okay.
And then 10 to 11. That
Okay.
11.
All right. Now let's run this. Okay.
That's wonderful. And that's at 50-50.
This is at 50-50.
75 balls.
Now, if you notice, that I guess you're right. That would be equivalent to 2, and this would be equivalent to 12, and this would be equivalent to 7. So, as expected, there are more 7s.
Yes.
Right? But you notice it's not completely symmetrical.
But if you double the number of balls.
All right, but now I'm going to take the balls up to a greater number. All right.
Yeah.
Let's go to a maximum of 1,000. Right.
And run it fast.
You want to run it?
Yeah.
Well.
Okay.
I can run it fast.
This is wonderful. Just leave it like that. This is wonderful.
So this is our model.
This is humankind.
Well, what if we call this area a causal world?
Yes.
We inhabit a causal world. We, at each of these junctures, are making a decision of whether we go left or right.
Okay.
We made the decision. We had the free will to do so.
Yes.
We may have made the decision by just tossing a coin. And the end result will be that pattern.
Yeah. More symmetrical now.
The end result will be this pattern. Where we will fall in that pattern, we don't know.
Okay.
All right?
No. Yeah, do it where it's not so fair.
All right. Now, what I'm going to do, I want to, before I do that, I want to show something else. I'm going to take the number of balls down to a lesser amount. Okay.
Mm-hmm.
And
how many?
I've got 282, and I'm going to do something else. I'm going to, all right, now watch.
What did you do?
Well, what I'm doing, it's showing the path that the balls went on. So each of those balls...
The biography of a particle.
That's right. It shows the path.
How did you get to be on the right-hand end?
Well, you can appreciate that there are a number of ways that any ball can get into a location. Mm-hmm. And if it so happens that the wealthiest people are over here, you can have many of them telling you their theory of how they got over there.
Yeah.
But all of them got over there, but the chances are from what they saw had nothing to do with their theory. Mm-hmm. Now here it is. If we live in here. Now if we had the ability to escape a causal land, what we would see is this.
Now what is this? What do you mean?
What we will see is this pattern being formed.
If we're standing back here above the distribution looking at it.
Well, let's call it worlds for a minute, because here is a world which is causal world, right?
Yes.
And here is a world that we're looking at from outside, and it's a causal world. Am I making myself clear?
No. When you say here, the first here.
Well,
what's the first here?
Let's assume that this is comparable to flat land.
Okay, so you're changing your point of reference.
And this is sphere land.
So the distribution at the bottom
is what someone in sphere land would see.
Okay. So if you're inside,
you don't see the
distribution.
You don't see the distribution
unless you change your frame of reference, do some measurement, and get out of it. That's what you're talking about. Not available to the senses.
It's not available. In the history of the world, what relates to this whole area of discovery. And by the way, it likely would not have furthered if Galton hadn't built a device like this. Mm-hmm. That what refers to this whole area of discovery is the fact that this is what is available to our senses. This is not. In the case of physics, the circle started from what's available to our senses, the moon and the sun. Mm-hmm. And that led to the wheel and gears, and ultimately to what isn't available to our senses, to pi. Similarly with magnets. Lodestone was available to our senses. This discovery is as important as those two other discoveries, with one major failing. It's not available to our senses, and that is playing havoc. It's playing havoc in other ways, in that we bring up our children in a causal land from the day they're born. Mm-hmm. They get so conditioned to a causal land that they cannot ever perceive the vast majority of a causal land. Mm-hmm. So what focusing on what children need has taught me is look for as many ways as possible to make a causal land as visible to the senses as the sun and the moon and lodestone. Now, a causal land is not a turn-on, the same way in history the sun and the moon has been a turn-on and lodestone has been a turn-on. Yeah. But if we now embody this in coinage, because as you can see, what this is, well, you may not see this, but what this is known as the binomial expansion. It's the end result of coin tossing. And how many times you toss the coin will give you this pattern. So when this subject matter is taught in all introductory courses, the professors or the teachers start off with coin tossing, and they start off with dice, which we'll go to in a moment. Mm-hmm. And I'm saying if we in turn build a coin a good luck coin that is ubiquitous. At least millions of children from the day they're born will be familiar with this curve from a fun standpoint.
Mm-hmm.
And
It
may
will change their way of thinking.
and it may very well change their way of thinking.
Mm-hmm.
So here we have, because of the wonderful aspect of the web, I can find people with similar interest. I can see what they're doing. What is sparse but not completely devoid is that there's not enough being done in terms of children. Mm-hmm. There's not enough being done.
Early age, you mean?
Very early age,
yeah.
right? We have a quotation that, well, I'll give you an example. Let's assume for a moment that, let's see what I can do. Let's see what I've written for a moment, okay?
I'll turn this off.
Yeah. Now this confusion of things I have on my front page or on my screen is only I haven't had a chance to put them away. Mm-hmm. But here are basically these essays that I write for myself to try to get it clear. But here I wrote this particular one. A causal is it a missing word and a referent that is essential for children to understand the unavoidable role of chance and luck in their lives. Mm-hmm. And I put this in passion statement, which I'm really in a way quite proud of, because I think it explains things.
Good.
So a revolution in thought has occurred in our knowledge of human behavior that ranks in importance with names such as Einstein, Darwin, and Newton. It has no comparable hero. It defies common sense to the same extent that the fourth dimension is not accessible to our senses, and appears on no list of the greatest discoveries in the history of man. Unfortunately, the revolution in thought is essential to all, is accessible to very few only after extensive and lengthy training, and these few have been singularly unsuccessful and frustrated in their inability to share with all that which they have perceived. One is reminded of the situation described in Plato's allegory of the cave, Abbott's flatland, and the blind man and the elephant. Now, I continue in this, and I give an introduction to Galton and what Galton, because Galton saw it, mm-hmm. And he built the device in order to show others. He has said, the invisible schemes are not, however, to be removed too soon from our imagination. It is always well to retain a clear geometric view of the facts when we are dealing with statistic problems, which abound with dangerous pitfalls easily overlooked by the unwary while they are cantering gaily along upon their arithmetic. What he missed when he said geometric, he himself didn't realize the contribution he made by inventing the causal. And geometric is not enough. You have to have the physical dynamic model to see what's going on. And all the teachers, despite the fact this is roughly 1889, and although you see the demonstration, by and large they have missed this in the teaching of this subject matter. I have a number of quotations here. Now here is the point that I made before. Now, Ephraim Fishbein, who was a researcher, unfortunately he died a few years ago, utilized a variation of the quincunx in his research on the intuitive sources of probabilistic thinking in children. You know, how do children think about chance? How did they learn it? Now, Piaget did this work. Fishbein did. There are people working in the literature, but not that many people are aware of it. Similarly, I'm interested in how do kids learn about money? Because in turn, we condition them on money. Mm-hmm. You just see a young child, the money doesn't mean anything to them. By the time they're a certain age, it means a lot to them. And we do it unconsciously, and frankly, we may be doing them a disservice if we don't realize how we're doing it. Now, here's what Fishbein had to say that is at the crux of a lot of what interests me. Fishbein surfaced another major problem to this day not addressed by educators, and I'm going to show the quotation. We condition our children from birth onwards on causality, but important things happen without any discernible cause and are yet predictable. No satisfactory word exists for the opposite of cause and causality. with a clear referent in English language and perhaps in other languages of the world. Not only is a word absent, is it possible that once conditioned on causality, our children as well as ourselves cannot undo the damage done and cannot see the opposite of causality and its importance to our survival?
Mm-hmm.
At present time, no meaningful words for the opposite to cause exist. Therefore, there is no, or is next to no discussion of the topic. Now, it's a non-problem for most of us. Well, that's not completely true. It's a philosophical problem, but I won't go into that now. Now, is there a causal the key that will unlock the door that hides the secret how luck works? I like to go on to Fishbein's quotation, intuition of probability. This discussion may be summarized thus. The synthesis of the stochastic, which means chance, probability, and the determined, which means causality, right? Mm-hmm. Which the concept of probability theoretically supposes, is to a certain extent prevented by the fact schools and the whole intellectual environment of the child conspire to favor only one of these terms, that of explanation by strict necessity, meaning strict causality, and create a cognitive set, imprinting, like the same way as you get imprinted on a religion, in this direction. The child is gradually and fundamentally convinced that to fully know and understand a phenomenon means referring to a unique causal relationship. This is a belief which has in fact dominated modern scientific thought for centuries, and that which is still cultivated in schools. If this explanation is correct, it poses an important educational problem. Is it useful for schools to go on cultivating this orientation exclusively, or would it be better to prepare the child early for the synthesis of the possible and the determined by providing familiarization with stochastic, that's chance phenomena, and the possibility of rationalizing them? We are not only referring here to the introduction of probability calculations to older children. This question has been in principle resolved, but also to the introduction of certain practical and theoretical problems of this type even to very young children. And that's in his Fishbein, The Intuitive Source of Probabilistic Thinking in Children, 1975. Now, in 1975, he translated Piaget's work, where Piaget was on the same trend, which Piaget had written in 1950. So we can see from the time of 1500 with the Chinese, then 1733 when the equation for that curve came in, to the era of quantum physics and relativity, where it became that much more important, is that we are dealing with a change in belief system, a change that is as dramatic as the introduction of a new faith, and with all the resistance that entails. So what I'm recommending is we look at this subject matter as if it was a faith, and set our prejudice aside between religion and science, and go at this subject matter as if it's faith, because the religion of psychology has brought to the forefront how faiths are established.
You said the religion of psychology.
It is a religion as well. I didn't mean to say it that way, but it's a good Freudian slip. So in the next quotation, let's see, it's not too long. Here is the frustration of the statistics teacher.
Is this Fishbein again?
No, this is Susan Lajoie. It's from a book, or it's her treatise, Identifying an Agenda for Statistics Instruction and Assessment from Kindergarten to Grade 12. And this is Reflection on Statistics, Learning and Teaching and Assessment in Grade 12. It's a compendium which she was an editor, and this happens to be a quotation by her. The widespread consensus among educators and researchers is that statistics education in its current form is inadequate. A discouraging finding regarding statistics is that most individuals have a limited understanding of the subject matter. Given that statistics instruction has generally restricted to those pursuing professional academic careers, this limited understanding is not surprising. What is discouraging, however, is the finding that a large proportion of university students fail to understand elementary statistical concepts even after taking several courses. Students' lack of conceptual understanding may be due, in part, to their having insufficient early exposure to statistics instruction. I'm suggesting much earlier than what she's talking about, before kindergarten. Not as instruction, but in games. This perception has led to the consideration of teaching statistics in the early grades. Because models of statistics instruction at the university level are quite sophisticated and not always effective, new approaches for teaching and assessing statistics from kindergarten to grade 12 must be developed. Statistics instruction must be redesigned to include activities that empower the student, are engaging, and provide students with opportunities for doing statistics and demonstrate relevance to real-world applications, I think, as we talked about at the beginning in the models. A problem-solving focus can help promote statistical understanding by providing students with opportunities to inquire, investigate, analyze, interpret, rather than to compute and memorize. Part of the difficulty with the statistic pedagogy from kindergarten to 12 is that the content is new for many teachers as it is for students. And I go on to other quotations that show that we're dealing with a revolution. It goes back to Ecclesiastes. I've seen something else under the sun. The race isn't to the swift or the battle to the strong, nor does the food come to the wise or wealth to the brilliant or favor to the learned, but time and chance happen to them all. Now the major difference is that since Ecclesiastes, we understand more how this happens. And the causal demonstration and modeling can show that. How much time do we have, Dave?
10 minutes.
All right, I'm going to go on to some other quotations.
Have you printed this out recently? Did you send this to me recently?
Yes. Well,
Okay.
you've had it over the last year.
Yeah,
But
okay.
I think it makes a lot of difference in going over it rather than just sending it to you in writing.
Yes, for sure.
Right. There's another dimension. Every person is born in a highly I'll start again. Every person born is a highly probabilistic creature, having been randomly put together by a chance selection from 23 chromosomes from each parent. The combinatorial variation is remarkable, even in extremely homogeneous populations, and even more so in multicultural populations where there are great disparity in the average abilities of different groups. And this is from a review of book, From Chance to Choice, Genetics and Justice, by a number of professors. Now this is interesting. What is clear beyond all scholasticism is this: the taming of chance and the erosion of determinism constitute one of the most revolutionary changes in the history of the human mind. I use the word revolutionary not as a scholar, but as a speaker of common English. If that change is not revolutionary, nothing is. That is the real justification for talk of a probabilistic revolution, 1800 to 1930. Now, Ian Hacking is a professor at the University of Toronto and also in France, and he was addressing himself to the question, was there a probabilistic revolution, 1900 to 1930? And it's in a compendium of two books on a conference held in the early 1980s for over a year, where the people who are in the forefront of this field got together. And the result was these two books, a compendium. And now, the fact exists, but where is anyone taught? I mean, we put Einstein on a pedestal, and rightly so. But Einstein, without what was found here, would never have gotten a Nobel Prize, because he has to dealt with Brownian motion, which led into the quantum physics, and in turn Brownian motion relates to what's found in random walk in the stock market. Now here, I'm going to give another quotation, because a number of the participants in this conference wanted to make what was said in the conference and is reported in this compendium more available to a larger audience. And some of the very brilliant people got together. And one of the interesting things, prior to this conference, there was a real shortage of books on the history of this material. After the conference, several of the participants, Porter, Stigler, Hacking, and such, I'll mention some others in a moment, they in turn wrote up very interesting histories. But it's surprising on a subject matter as important as this that it's only in the 1880s, 1980s, 1990s that any major history, there were compendiums. But all right, here is a quotation from The Empire of Chance, which these people put together to try to convey it to a larger audience. We analyze how probability and statistics transformed our ideas of nature, mind, and society. That's quite a statement. These transformations have been profound and wide-ranging, changing the structure of power as well as of knowledge. They have shaped modern bureaucracy as well as modern science. The extraordinary range and significance of these transformations has rarely been appreciated, perhaps because the influence of probability on the various sciences has until now been studied piecemeal. Also, the domain of probability and statistics was less often expanded by decisive conquest and revolution than by infiltration and alliance. In this book, we view these transformations synoptically as a single historical movement, one whose influence on modern thought and life is second to no other area of scientific endeavor. All 6 of us were members of a year-long research project, the Probabilistic Revolution, at the Center for Interdisciplinary Studies in Bielefeld, Federal Republic of Germany. Essays written by participants in this project now fill 2 thick volumes, and they state that. Now, all of the essays couldn't get in, and Ian Hacking gave me those that didn't. So I have those as well, that demonstrate the importance of the topic across a wide range of fields, nations, and centuries. Our subset of 6 hope to condense and connect the elements contained in these essays into a single narrative, one that viewed the growth of probabilistic and statistical ideas from a unified perspective. Now, they did an excellent job, but again, it's not intelligible to a man on the street.
What is the subset of 6? 6 what?
People. Here they are. All right, Gerd Gigerenzer, and Zeno Switchnik, Theodore Porter, he's written the history. Lorraine Daston has. John Beatty, I don't know. And Lorenz Kruger unfortunately died, and he was the instigator. He and Ian Hacking were the instigator of this conference.
Beautiful.
And this quotation is rather lengthy, but it is really the sentiment of the vast majority of people who have been subjected to this subject matter. And note, I think we'll read it, because what you will get from this is, I think you will almost get the sense that there's a theological dedication to this, and a new faith. Statistics has not been part of a typical liberal arts curriculum. After an examination of some central features of both liberal arts education and statistics, it is argued that statistics can play a strong role in a liberal arts education, in part because of the advances that have taken place in computer technology. We've seen some of that today. For many statisticians, our field becomes more than rules of methods of dealing with data. It becomes a way of acting and thinking about the world. I say our religion, right? We live in a stochastic world where events are governed by complex structures of probabilities. All of the seemingly random events that take place around us in our social, biological, and physical world make a confused and chaotic picture. This is the view within causal land. But there are regularities in randomness, and it is statistics that enable us to study and gain understanding of these regularities. That's the view from a causal land, right? Statisticians realize this, and we use statistical methods in our professional lives to help scientists and policymakers in their work. But more than that, statistical training contributes to an understanding of the world around us, the same way as our religions do. The ability to live and function with limited information is an important lesson learned from statistics. Rarely do we have complete information that would seem necessary for perfect inference about the world. Decisions and inferences are based instead on limited and incomplete information, and statistics teaches us how to live with and use the available information. Knowledge of statistics offers a person a better way to understand and therefore a better way to deal with the uncertainties that surround us in our daily lives. In short, statistics concerns itself with how we can gain from limited information an understanding of seemingly random world around us. According to this view, statistics is essential for our understanding of the empirical world. If the purpose of liberal arts education is to prepare us to function as members of society, it follows that statistics is an essential part of liberal arts education. We need to teach more statistical thinking and less statistical methodology, and that's what they're doing today, is the methodology and not this wonderful discovery. When teaching statistics as part of a liberal arts curriculum, what happens now is that our concern with methods does not leave room for the students to develop the ability to think about the world in a statistical way. And I will add that they don't teach it historically, so they don't know the blood, sweat, and tears that have gone into getting here. And they have to go through the process. Only over a period of time did all these various methods and techniques come together in a stochastic view of the world and of the role played by statistics in providing an understanding of how this world functions. Perhaps in our teaching of statistics to liberal arts students, it is time to shorten the path through the methods and get directly to the heart of statistics. Basically, that if you don't have this view of the world, then the decisions you're making as a politician, as a person voting, or anything else are apt to be fallacious. One particular reason why this may be more feasible now, in a way that was not just a few years ago, is the progress that has been made in statistical computing, some of which you're seeing. The statistical computer package have become so useful-friendly that they can be used with minimum instruction. The changes now possible in our teaching can be liberal as well as dangerous. In conclusion,
liberating as well as dangerous.
Yes, I'm sorry. In conclusion, statistics has much to offer to liberal arts education. Liberal arts education is not a static list of classical subjects. It is an education offering the best of what the arts and sciences, including statistics, currently provide, so that students can develop an understanding of themselves and society in that which we live. This is Ivan Gudmund, Statistics in the Liberal Arts Education, the American Statistician, February 1985.